Oh, so it's 10:35. We got 6 people here. So I guess let's do it. So we're going to talk about the Lucas imperfect information model today. I have a Kahoot. We have the Q&A session, and then I'll talk about the first problem from problem set 3. So
do you hear us?
Yeah, I can hear you.
Great. Yeah. And we can ask you questions.
Yes, absolutely. That's an important part. That's actually half of question and answer.
Yeah.
So yeah. All right. Well, let's do it, I guess. Let's share the screen for the Kahoot. Teach. So I have something else at 2:30 today. I don't think it doesn't. Our classes don't usually last that long, but if we have time, I also want to talk about something about the pandemic and the way the vaccines are being distributed, and how it's similar to the trolley car problem, if you've heard that before. But let's do this stuff first. One, 2, 3, 4, 5. 5th person want to sign up? Okay. Alrighty. Let me just double check here. Let's do it. Okay, so what do we call the 2 household members? Producer shopper, principal agent, manager supplier, or buyer seller? Yes, wow, you guys came well prepared today. Very well done. Oops, I should have let you see that. In the Lucas model, why do we only have an internal labor market? Simplifies the problem, not that important. Households must choose labor hours, trying to model family-owned firms, or wage contains information on aggregate production. Yeah, so this one. So let's see here. 3 of you answered households must choose labor hours. Well, it's true that households must choose labor hours in the model, but it's not why. It's not like the key reason why we want to have the family-owned firms or the internal labor market. You know, households could still choose labor hours if they were working for another firm. So the reason why is because an important part of this Lucas information model is how information flows around the economy. And the issue is you don't want the household firms, like the producers in the household, to know what the aggregate level of prices is in the economy. So if they could see the wage, that would contain information about what the aggregate price level is in the economy. So we have to kind of shield them from observing any information about that, so they can't see the wage. So that's the idea. Okay. All right, in the Lucas model equilibrium, are all households equally well off? Yes or no? Okay, we got an even split. So the correct answer here is no. And the reason why is because there's this demand shock, right? So, you know, ex post, some of the households are going to have a positive demand shock. That's the Z in the model. And some will have a negative demand shock. So some will be better off and worse off depending on just how much the market likes that product. So there is this built-in sort of ex post heterogeneity among households. So that's the answer. Stop me if there's any questions, of course. If there's no imperfect information, then is the equilibrium socially optimal? Pareto optimal? Is production socially optimal? Yes or no? Okay, so the answer is yes, and it's a bit tricky because we have firms in this model with market power. So I could see how you could answer no here. The reason, and I should be careful here, I hope I'm not giving away anything for later questions, but the reason is that the firms here aren't choosing their price, right? They take the prices as given. So even though there is, quote, market power, since the firms aren't actually choosing the price level, then the market power doesn't create any distortions. So that's
and just student, I think this is difficult because there's a double negative in the first line. So it is perfect information.
Yes, yeah, exactly. Yeah, exactly. I got that. If very good, thank you. If perfect information, then is production socially optimal? Yeah. So exactly. But anyway, yeah, the reason is what I said, but maybe I could have worded this question more clearly. Typically, if you think back to our Romer model, in that model, there was perfect information, but there was too little production. And the reason why was because the firms have market power when they set prices. The old monopolist problem, right? You set the price too high in order to make a higher profit, or you set equivalently, you set the quantity too low. Each household monopoly has a monopoly on its own variety. Why are there no distortions? Whoops. Is it because no external labor market, household and firm are the same, perfect substitutability between varieties, or households take prices as given? Yeah, so I should have remembered this because I actually just looked through these questions just before before I logged on, and that's why I kind of, when I said it, I said I hope I'm not giving anything away. But there you go. Does every firm produce the same amount in the Lucas model equilibrium? Exactly. No, because they all get these demand shocks, and based on the demand shock they get, it's going to change how much they produce. Oops, I should have let that run. Monetary policy is more effective when the variance of money shocks is small. True or false? Or indeterminate. Monetary policy is more effective when the variance of money shocks is small. Okay, true. Why is that? So at the very end of the slides here, I can write something again. Okay, draw. At the very end of the slides, we had something like, let's see here, output is equal to, I believe it was VZ divided by VZ plus VM times M minus expected M. Right, so you could think about it sort of, this is monetary policy. We're printing money more than people expect, or printing less than people expect. How's that going to affect output? Well, it's going to depend on this term here. And what is this term? It's the variance of the individual demand shocks divided by the variance of individual demand shocks plus the variance of monetary of money, if you like here. So if the variance of money is large, this whole thing is close to 0. If the variance of money is small, then this whole thing is close to 1. So you could think of this as saying that the monetary policy is more effective when the variance of money shocks is small. That's the math. And then you could also think about the intuition, which is that, if the price level is always kind of what we expect, then, if I see a shock, suddenly everybody wants the price that my goods are selling for is very high. It's unlikely to be because of money being printed or suddenly a bunch of money appeared in the economy, since, I know that the variation in money is very small. So, so then I infer that it must be my own demand shock. Okay, so that's kind of the intuition there. Okay. Last question. According to the Lucas model, does high inflation make monetary policy less effective? All right, so this is a bit of a trick question. So, as long as people expect the inflation to be high, then then monetary policy won't be affected by inflation. So as you recall, I mean, it's kind of a one-time model. It's like so it's hard to think about inflation in the model. But as I just wrote a second ago, just write one more time. So, if we think about M minus the expectation of M as being monetary policy, if everybody expects inflation, then they all expect this M to be going up every period. But it doesn't really affect how effective monetary policy is, because the government can print even more than the people expect. Okay, so you'll actually see that if you looked at the book or the slides, I think one of the slides had something like they plotted. It was something about the variance of nominal GDP on one axis, and on the other axis, it was something about, I want to say, I should actually see what it was, but it's something about sort of the effectiveness of monetary policy. So what really matters is how much something is fluctuating relative to trend. Yeah, so it was a bit of a trick question. I know that I can see why you answered yes here, but the idea is that it's surprises relative to expectations. So high inflation by itself doesn't cause ineffectiveness for monetary policy. It's when there's lots of changes in the money supply all the time. That's what does it. So yeah, so that's the Kahoot. Let's tally up the score. Well done. Yes. Nice. Late joiner. And KG. Okay. All right. Oops. So that's that. So let me pull up the slides. Let me turn off this thing. I'll reshare my screen. Oh, it's over here. That's why. So let's actually jump here to the end and see okay, this one. Standard deviation of a nominal GDP growth, okay, versus tau. And here tau is what? Did I find that somewhere down here? Oh, okay. Progress real on nominal GDP by country. So I guess this would be real GDP, and this would be the variance of nominal GDP growth. Okay, so again, this is nominal GDP growth. So you could think about inflation as being the growth rate. If it's constant, suppose, I mean, of course, this is a crude measure of inflation, but if the growth rate is constant, then there should be a very low standard deviation here. Whereas if you have lots of fluctuations, that is like there's lots of changes in the money level relative to a trend. So yeah, I should have looked at I watched my slides yesterday. I watched myself talk, and I can't remember what the definition of tau was. But I guess this is saying that, oh, I see. Okay, so we regress real GDP on nominal GDP by country. So we see sort of tau is like the effectiveness of monetary policy, if you like. So, when government is printing a bunch of money, do we see an uptick in real GDP? When the government is destroying a bunch of money, do we see a downtick in real GDP? That's tau. So tau is like the effectiveness of monetary policies, I keep saying. Okay, so in countries where we have a low standard deviation of nominal GDP growth, those are countries where we have relatively effective monetary policy. Okay. All right, we are now in the question and answer section of the lesson today. So anybody got any questions?
Hi, on slide 10 out of 22, you say in the videos that we use this average of z and that we know that z is equal to 1. Could you explain why we know that usually? I mean, is it because we add it into the consumption? So we add and subtract something and that's 1 in the beginning, or how do we come up with?
Yeah, hold on a second. Let me just quick change this. So if I understand what you're saying is you're asking why we can take averages and get that the average z is 0. Is that the question?
Yeah, and in the videos you say it's because we know from before that the capital Z is 1 in total, sort of. So is it because some lose and some win, or that is my question? That's
right. Yeah, so so Z is the demand for it's like the demand shock for your good. And then we're gonna assume that on average this is 1. So so Y is kind of like the average, if you like, amount that is spent on every good. And then we're gonna have this Z be higher for some firms and lower for other firms, so that, if I started to integrate over all of the different Z shocks, I'd still end up with just Y. Does that make sense? So we do want Z to sort of be 1 on average and then be distributed. So Z has an I subscript, meaning that, as you said, some producers are going to get a high Z, some are going to get a low Z, but on average, it's going to be 1.
Okay, yeah, I think I got it. So it's because if we would have 1, then it would just be like output. It would not make any difference if we had Z or not.
Exactly, yeah. Well, we definitely want firms to have these demand shocks because that's the thing that they want to respond to, right? If suddenly it's like they're more productive this period, they are going to want to produce more. And if they're less productive, they're going to want to produce less. So, yeah. And you can think of it as shifting the demand curve in like a monopolist model. So, if you shift the demand curve out, then the firm is going to want to produce more. If you shift the demand curve in, then the firm is going to want to produce less. And the ZI is kind of like how far out you shift the demand curve. And then, of course, because we're taking logs, then the the log of 1 is 0. So there's, as I said in the video, there's a bit of hand waving here because there's a distribution, right? So the expectation of a distribution that is mean 1 doesn't imply that the expectation of the log of the distribution is mean 0. That takes some additional assumptions, but we're going to assume that those things are true. Certainly the log of 1 is 0. And like, as I said in the Kahoot as well, this Z is why each firm in equilibrium is going to produce a different amount. It's why each household is they're not all going to have the same income in equilibrium, because there will be some high draws of ZI and there will be some low draws of ZI. And the firms that get high draws are going to produce more, and the firms that get low draws are going to produce less. They don't know for sure what their ZI is, right? Because they can't differentiate it between, they can't differentiate perfectly between the overall price level shock, the money shock, and the demand shock, but they will react to a demand shock.
In your slides, you don't talk about the Lucas critique, as you mentioned in the book Romer. Is that so you can ask it on the test or in like one of the assignments?
Yeah, probably. No, I didn't. I actually didn't realize. I didn't go back and reread the chapter, but does he talk about the Lucas critique?
Yeah, it comes when he talks about expectation and the Phillips curve.
Yeah, exactly. So if we kind of go down to the end, we have this Phillips curve, and it's called this expectation augmented Phillips curve. Let's see where I talk about it. Yeah, so I guess if we say it here. This isn't, yeah, it's not quite right though, because, you know, the Phillips curve is the relationship between inflation and unemployment. So, you know, you guys all took macro 101s, you know, but I'll just draw it here and say a couple words about it. Okay, so traditional Phillips curve, it's going to be, let's say, unemployment down here. And here we're going to have inflation, which is usually called pi. And in traditional kind of macro 101, you learned that the Phillips curve is downward sloping. So it means we have a choice. We can either have lower unemployment and higher inflation, or we can have higher unemployment and lower inflation. And then you might think that those are things that the central bank wants both of them. So there's a trade-off there. In fact, there's an economist named Art Oken that in my other class, we just read some part of the book he wrote, but this was his big thing, is that there's this trade-off between inflation and unemployment. Now, this thing here, we're calling this an expectation augmented Phillips curve. So let's think about how that's related to this thing, the traditional Phillips curve. I don't know if they talked about this in the book, but let me actually just erase that. And I'll keep it on there so you can look at it for reference. And then I'll change the color though. Okay, so let's draw a new curve. Now, if you think about unemployment, let's think about a very simple model of the economy. Forget about capital. Okay, well then unemployment is just kind of the inverse of production. If labor is the only factor, then it's like if you have lower unemployment, then you have higher production because you've got more of your resources, more of your labor is employed in production. If you've got lower unemployment, you've got higher production. If you've got higher unemployment, you've got lower production. Okay, so we can actually kind of inversely relate unemployment and production. They're kind of flip sides of the same coin, right? And then let's think about this inflation, but rather than inflation, let's think about deviations between the money supply and the expected money supply. So again, it's not just growth of M, it's growth of M, or it's M relative to expectations. Okay, so up here now we're going to have sort of M minus expectations of M. Okay, so and now because we flipped, right, here we have unemployment. Well, when unemployment is higher, then production is lower. So actually this is going to be a positively sloped curve, okay, because output is the inverse of unemployment. Okay, so these two curves are very closely related. That's why we're calling them both Phillips curves, right? This one is the traditional Keynesian macro 101 version of the Phillips curve. This one is the sort of Lucas imperfect information model version of the Phillips curve, but they're both sort of plotting something that's very closely related. All right, now where do we get into the Lucas critique? So what's the need? You know, we already have this thing. We all took macro 101. We already know this Phillips curve. Why are we trying to make it more complicated with this, with all this expectations and stuff going on in this model? Well, the reason why is because this Phillips curve is just a statistical relationship. Okay, so what happened was, and this is a bit of a caricature, a bit of a cartoon, but it's sort of a famous macro 101 story. So maybe you've heard it before. So the idea is that for like the 1940s and 50s and 60s, if you were to actually plot like year by year, the inflation levels and the unemployment levels, they traced out a downward sloping curve. So, I could put maybe 1945, or that's bad for World War II. Let's say 1947 in the United States, maybe it was here. And then maybe in 1953, they had a little bit lower inflation, but they had higher unemployment. So maybe it was there. And in 1961, well, then they had really high inflation, but they had really low unemployment, something like that. So, you just each year you're going to put a dot, and then if you kind of trace it out, it's going to look like this downward sloping curve, right? So actually in this period, this is kind of another interesting little wrinkle, another little point in the story, part of this legendary story from economics. Milton Friedman and some other economists at the time that were part of this Chicago school actually predicted in like the late 1960s that this Phillips curve relationship was going to break down. And the reason they said it was going to break down was because for a long time, in order to keep unemployment low, or alternatively GDP high, the government kept printing lots of money. So inflation was high, and it remained high for like lots of like the 1960s. And the idea is, now think through the lens of the Lucas information model. If you keep printing money every year, it's like inflation is really, really high. Eventually the firms get wise and they say, guess what? Well, they printed money, the money supply was much higher every year for the last N number of years. I bet it's going to be higher next year too. So they expected inflation. And then if they expect inflation, in order to keep unemployment low, you have to even print more money. So you have this sort of the central banks start losing control over the economy, and then the Phillips curve breaks down in short. So then if you look in the 1970s, now let's choose another color. So in the 1970s, you ended up having years that were like this, like out here, 1973, 1971, 1974, whatever, 1976, where you had both high unemployment and high inflation. And now if you draw a line, it's looking more positively sloped than negatively sloped. So now all the central bankers are worrying, oh my gosh, what are we going to do? We don't know what to do. We previously, if we wanted lower unemployment, we just print more money and it worked. And now it's not working. We have stagflation, they called it, that economic stagnation and also high inflation. So that was sort of the context where this Chicago school started saying, well, what's really critical is you need to model not at the level of statistical, not at the level of macroeconomic statistical relationships like inflation and unemployment. You need to think about what households are expecting themselves, households and firms. And why is that? Well, it's because if you change your policy, you're not going to change technology. Okay, it's like there's a certain way of making a cake. You can do whatever you want. You can change, you can say eggs are cheaper and sugar is more expensive, but the technology for making a cake hasn't changed. You're still choosing from a menu of ways to make a cake. So you want to write down the production function. So that's one thing. I think in the Lucas model, we have a production function. It says that output is equal to labor. That's production function. Doesn't matter what the government does. Doesn't matter if it prints money or whatever it does. It's still output is equal to labor supply in this model. All right. You also need to model preferences because, whether I prefer red or blue, what's your favorite color? It doesn't matter whether the government prints money or not. So, in the Lucas model, people aren't making preferences about colors, but they're making preferences about trade-offs between consumption and labor supply. The government can print money however they want. It's not going to change the fundamental preferences that households have. Okay, so the idea of the Lucas critique was you can't model based on these macroeconomic variables. You need to model based on these low-level things that don't change, that are policy invariant. So that's what this model did. This was one of the first models to do that. And you end up with something that's similar to the Phillips curve, but not quite the same. And how is it not quite the same? Well, we end up having expectations here, okay? And that kind of changes everything. So now, why are these green dots out here? Well, it's because people expected the inflation to be really high. They didn't trust that the central bank would keep inflation low. So That's the famous Lucas critique. You can't make policy predictions by looking at statistical relationships among aggregate variables. You need to model at a low level. And I hope that's what the book said too.
Do you want me to read it?
No, it's okay. Did you want me to open it up? Did they say something different?
No.
Okay. No. I have a copy, actually, a PDF copy of the textbook. Any other questions?
Think this is one of the reasons why economists kind of drew a line in the sand and put the politics on the other side, then just took over the central bank, and why MMT economics doesn't work.
Yeah, I think that's right. So, you know, it's kind of funny if you look at the way that the evolution of sort of theory about central banking sort of progressed. So in like the 1960s and 50s and 40s, it was very heavily influenced by Keynesianism, like the old style Keynesianism, which is basically the Phillips curve. And then in like the 1980s and 90s and 2000s, that was this sort of triumph era of sort of new expectations, you know, Lucas critique style, micro-founded models. And, you know, I think there was a lot of triumphalism there as well, in the sense that, oh, we figured everything out, great moderation. And it's true, if you look at sort of until the Great Recession, you know, there was very little economic fluctuation for the 1980s and 90s in quote developed sort of Western countries. But then the Great Recession now has made people rethink a lot of the way that they think about these sort of models as well. So that's true. And just to touch on one of the other points, there's this big thing starting in, like, say, the 1980s about central bank independence. So, you know, there's this political business cycle, the idea that when politicians are close to an election, they'll want to print more money to boost GDP just before the election. And there's some evidence that does happen. So there was this big push that central banks should be independent. And, you know, there's a big should there, right? So sometimes it's hard to argue should from is. But what it means is that central banks and monetary policy was actually quite disconnected from politics, from democratic politics. So, like, there was very little accountability among central bankers. And, you know, that's not necessarily a good thing. It relates more deeply to issues about whether technocrats are the best people to run the government. It's not always so clear that that's true, but that's all I'll say about that.
Yeah, can I tell you a story, all of you, about Iceland and the central bank there?
Sure.
Because historically, Iceland had like 3 central bank managers who were part of like 2 different parties, and then one who was like a professional-ish. Anyway, so it was always a political position in Iceland. So like the guy who was the prime minister of Iceland from 91 to 2005, he became the central bank manager after 2005 and until 2009 in the collapse, right? So yeah. In Iceland, this has always been like a political position. And it wasn't until after the collapse that I think that people realized that maybe that wasn't smart.
So they changed it.
Yeah, they changed it, and they changed it from 3 managers to only 1, and he was the ruler, and he could be fired by the government, which of course the political guy couldn't be fired because he was assigned there by, you know, it was his retirement job in a way.
Interesting. Well, you know, the
so
Iceland had a rough,
or was let go. Yeah. Well, when he quit and was let go in 2009, he went to work for the main paper of Iceland. So, you know, it all goes around.
Yeah, I won't say, you know, Iceland had a pretty rough Great Recession, but so did the United States and the EU, which both had independent central bank heads. So, you know, it's not necessarily so much better or worse. But and you know, also Janet Yellen, I don't know if you heard this, but the last central bank head before the current one, after she left, she's been like giving these very fancy talks where she gets paid like, you know, $200,000 to give a talk for, you know, Goldman Sachs. And now she's the Treasury Secretary. So there you go. All right. So any other questions about the model, the Lucas information model? Let me just say one more thing too while you're thinking of potential questions. So there was something I said last time, which you'll notice hopefully was true about this model, which is in both the menu cost model and also the Lucas information model, you'll notice that a lot has to do with surprise, right? If people expect what monetary policy is going to do, then at least in these models, then the monetary policy has no effect. So it's only surprises that actually have an effect. And it's kind of an interesting point. And if you follow sort of what like central bankers talk about, there's like a type of central banker that wants to follow a rule. So for instance, you've got, oh, I'm totally blanking out on the guy's name. This really common rule for oh, it's not Phillips. What is that guy's name? A common rule for monetary policy. Hold on a second. What's here? This way. I'm not going to remember it, but we're actually going to talk about it in the
We're talking about
TSG.
discrete versus commitment.
Yeah, well, exactly. So, you know, if you're committed to like a rule, then according to these models, nothing happens. Everybody can see the data that goes into your rule, and if they know your rule, then there's no surprises. So, according to these models, that sort of monetary policy should have no effect at all. It's annoying to me. I can't remember this guy's name. But anyway, any other questions? Okay, if there's no other questions, then let's take a 10-minute break, and then I will solve the first problem from problem set 3. Oops, this. Okay, we are back. So let's take a look at problem set 3. So this one only had 3 questions. The first one was this RBC question. That's part of the reason why some people pointed out that we actually covered the Lucas imperfect information model today, but I thought it would be so little without that, this problem set, and this 6.16 was a relatively short question. And then the other thing as well is that for the next problem set, I usually like to have at least part or most of it to be a mock exam, which I think I will follow again this year. So then there's no room to put that on. But anyway, whatever. So today, let's solve RBC 5.8, and we can scroll down here to see it's this thing. Let me make it a little bigger. See what it says. So it's a simplified real business cycle model with additive technology shocks developed by Olivier Blanchard and Fisher. I don't know his first name, 1989. So it's a economy with a constant, already the first difference, population of infinitely lived individuals. The representative individual, so they're all the same, maximizes the expected value of this thing, all right? Which you can see is just a utility function and then divided by 1 plus beta to the power t. So that's a discount factor, rho is the discount rate. We're going to assume that the instantaneous utility function looks like this, which is quadratic utility, which is simple to work with, and you're going to see why, actually, when we start solving this, this model. But you can see it's quadratic, and it has a weird feature, which is that as consumption gets larger and larger, you can see that eventually that this quadratic term is going to dominate whatever you choose for theta. Eventually, this quadratic term is going to dominate the linear term. So eventually, your utility function is actually going to be decreasing in consumption. That's the bad part. That's why that's the bad part of this utility function. And you can see that they're going to assume here that we're always in the range of utility where u prime is positive. So meaning that we're always going to assume we're on the upward sloping part of this parabola that is the utility function here. It's a bit weird, right? There's a bliss point. There's a maximum level of consumption where you don't want to, if you go beyond that, you actually get less utility out of it. Or so another way to say it is you prefer to have lower consumption rather than higher after a certain point. But we're going to assume that we're not at that point, and then we can take advantage of the nice property of this quadratic utility you're going to see in just one moment. Okay, output's going to be linear and capital. Plus some sort of shock, okay? And the shock is time specific, but not specific to individuals in this economy. There's no depreciation, so another simplification, which means that what's the capital at time t plus 1? Well, it's just the capital at time t plus the amount that we produced minus the amount that we consumed. Okay, so it's kind of like our savings plus the amount of capital we had last period. Also, this was another strong assumption, actually. We're going to assume we're not going to derive, well, I say that, it's not quite right. The interest rate is going to be A. I say we're assuming it, but actually it's the same, because you look at the derivative of y with respect to k, you can see that it's going to be A. Okay, so there's one factor of production, it's capital, and the marginal product of capital is A. So the interest rate is A, okay? So it's not really an assumption, it's almost a result. Now here's the assumption. We're gonna assume that A is equal to rho. Okay, so what is rho? Rho is this discount factor. So we're gonna assume that just so happens in this economy that the interest rate is exactly equal to the subjective discount factor. There's no good reason for that. That's just what it happens to be in this economy, okay? Right, it's kind of like happenstance. This technology just happens to line up with this subjective discount rate. All right, we're going to assume that this E here, it's not a white noise disturbance. It's not an IID disturbance. This ET here is going to follow a process. It's going to be an autoregressive process where ET today is going to be phi times ET yesterday plus some white noise disturbance. So it means that shocks are going to have some persistence, right? If we get a high productivity shock today, then it's likely that tomorrow is also going to have a relatively high productivity shock. You can see that this phi is between -1 and 1. Okay, if it's 1, it's a random walk. If it's -1, it's a funny looking random walk. And if it's less, then it means that there's reversion to the mean, anywhere between -1 and 1. If it's -1, then it means it's flipping up and down. If I was productive yesterday, then I'll be unproductive today and then productive the next day. So typically you're going to assume that it's between 0 and 1. But yeah, okay. So we need to find, for part A, let's just look at the problems here. The first order conditions, which is the Euler equation relating CT to CT plus 1. And then we're going to do some more stuff, but let's start with that one. Okay. So we're going to do this the way the book does it, which is a bit hand wavy, but we're going to do that anyway. I'll take my notes out here. All right, so we're going to use the so-called variation argument. Can I make my little thing look like a pencil? No, that's okay. Okay, so parts, oops. So part A, we're going to use variation argument. Okay, this is what they use in the book, in the RBC model. So the argument is, if we're at the optimum level of consumption, then if we take a little bit of consumption away from people in one period and give it to them in the next period, we can't make them better off. Because if we could, then we weren't at the optimum. Okay, so we're going to argue that, that at the optimum, we have to be able to, if we take something from you today and give it to you tomorrow, that will make you worse off. The same thing is true that at the optimum, if we take something from tomorrow and give it to you today, that will also make you worse off. Okay, so we're going to use that as the argument to find this Euler equation. So the general way to write it is that U prime of CT times delta CT, let's just call this delta C. So we're going to find out, how does your utility change if we take away delta C from you today? Well, for a small delta C, a small change in C, it's just going to be the marginal utility of at CT. And then of course we're taking it away, so it's negative times this delta C. Okay. Now we're going to give it to you tomorrow. Okay, so we're taking it away from you today, giving it to you tomorrow. Of course, we don't know exactly what's going to happen tomorrow because there's this shock in productivity that we don't know what's going to happen with that shock. So so actually, I say that, but there's typically an expectation here, although I see that actually we're going to not have to worry about this expectation. Oh no, I still have to worry about it. Okay, there's an expectation here. And then we've got 1 plus A times delta C. That's what we get back. And the reason why I said, do we need an expectation here, is because 1 plus A, we know that's not related to this shock. That's always the same. The interest rate in this model is always the same. That's not true in the RBC model we looked at in the book. So anyway, how much are we going to get? 1 plus A times delta C. That's how much we get if we take if we take delta C away from you. I noticed I did something that I shouldn't have done here. So what's the utility? I'm going to add these things. This is my the utility cost of me losing a bit of consumption in this period. Now, what's the utility cost of, or utility benefit of gaining a bit of consumption in this period? Well, it's going to be 1 plus A times delta C. And then I have to discount, because I don't care about myself as much tomorrow, times U prime of CT plus 1. Okay. This has to equal 0 at the optimum. I can't either gain or lose utility at the optimum from making this trade. Okay. So you can see that I can cross out these. Let's start doing that. I can cross out these delta C's. There's no uncertainty there. It's just a constant. Okay. And actually this 1 plus A and this 1 plus rho, I can take them out in front because those are just numbers. There's no uncertainty about them. So I can take them outside of the expectation. So let's do that on the next line. So I'm going to get U prime of CT is equal to 1 plus A divided by 1 plus rho times U prime of CT plus 1, right? Expectation. There is an expectation here. Expectation of U prime of CT plus 1. Okay, now let's start doing a little bit more. We can again cross something out. In this model, we've assumed that A is equal to rho. So actually, this term goes away. Okay, so then we're left with just these two terms. So let's look at what U prime of CT is in this model. What is U prime of CT? Well, yeah, let's do that first. So let me actually erase that dot. You'll recall that U of CT is equal to CT minus theta times CT squared. Okay, so U prime of CT is equal to 1 minus 2 theta CT. Okay, so why is this a convenient model to work with? It's convenient because the marginal utility is linear. It's linear in C. Okay, so that makes our life easier. How does it make it easier? Well, let's plug this in up here. So we get 1 minus 2 times theta CT is equal to the expectation of 1 minus 2 theta CT plus 1. Okay, expectation is linear, which means we can split the expectation between these two things, which means that we can cancel out the 1s. We can multiply both sides by -1, cancel those guys out. We can cancel out the 2s, and we can cancel out the thetas. We can divide both sides by these as well. So what do we end up with? We end up with CT is equal to the expectation of CT plus 1. Okay, so in this model, the Euler equation is CT is equal to the expectation of CT plus 1. So in other words, what you consume today, you consume the expectation of what you're going to consume tomorrow. Okay, and that's the end of A. Any questions about that? Okay, if not, let's look at part B. Guess that consumption takes the form CT is equal to alpha plus beta KT plus gamma ET. Given that guess, what is KT plus 1 as a function of KT and ET? Okay, so let's just write this down over here so you can remember. Part B, we're going to guess that CT is equal to alpha plus beta KT plus gamma ET, beta KT plus gamma ET. So we have no reason for expecting this. We're just going to guess it and then see if that works, if we can actually find an equilibrium with this type of guess for the consumption levels. Okay, so we also know from the problem that KT plus 1 is equal to YT minus CT plus KT. Remember, there's no depreciation. So what is my capital tomorrow? Well, it's my capital today plus my savings, which could be positive or negative, right? I can have positive savings or negative savings. Okay, so the problem wants us to derive KT plus 1 as a function of KT and ET. Okay, so we have up here CT as a function of KT and ET. We also need YT as a function of KT and ET. But luckily from the problem, we have that YT is equal to A KT plus ET. Okay, so all we have, I mean, this one is not much of a problem. We just have to plug in our definition of y here and a definition of c here. So let's do that. So we get k t plus 1 is equal to a kt plus et minus now alpha plus beta kt plus gamma et, and then add the last et there. Okay. Now that's it, right? We're kind of done, but let's make it look a little nicer. Let's collect terms. So let's put all the KTs together and all the ETs together. Okay, so let's rewrite this now. KT plus 1 is equal to only one alpha here. So there's going to be a negative alpha. Okay. Let's look at everything that's multiplying KT. We've got an A and we've got a negative beta. That looks like it. So then we've got plus A minus beta. Ooh, I feel like I'm missing something from what I solved earlier. Oh, there's also a plus. This is the, this should have been a, right. So I substituted wrong here. We've got, this was the YT, this is the CT, and then I put ET here. This should have been KT. Let me just erase that and put a KT. To match that, this one here. Okay, so now we have, as you see in A, we've got a negative beta and we've got a 1. Okay, so plus 1 times KT. Here we've got a 1. Here we've got a negative gamma. So we've got plus 1 minus gamma times ET. Okay, and that's it, right? So now we've got KT, it's a function of, KT plus 1 is a function of KT and ET, and then just this constant. And I believe that is all we have to do for that part B. KT plus 1 is a function of KT and ET. Let me know if you have any questions about that. Otherwise, I'll just keep going. Okay, what values must the parameters alpha, beta, and gamma have for the first order condition in part A to be satisfied for all values of KT and ET? Okay, so what CT wants us to do is, C wants us to do, I should say, CT, is it just wants us to put our definitions for the for CT into this first order this Euler equation. Double check to make sure. Yeah, that's right. Okay, and you'll see why that's why we needed the definition of KT plus 1. Okay, so recall that we derived that CT is equal to the expectation of CT plus 1. Okay, now let's just write our guess in here. So we've got alpha plus beta KT plus gamma ET is equal to the expectation of alpha plus beta KT plus 1 plus gamma ET plus 1. Okay. All right. Now, before I start getting messy, you can see that we actually up here have KT plus 1. That's in terms of KT and ET. Okay, so that's going to help us here. So I'm going to substitute this thing out in a second. But before I do that, let's actually deal with ET plus 1 here. So from the definition of ET plus 1, you'll recall that we had something like ET plus 1 is equal to phi times ET plus, I think that's some sort of epsilon t. Okay, and this thing was white noise. And then this thing is sort of how much influence yesterday's shock has on today's shock. Okay, so if we take the expectation of this thing on both sides, you'll see that this thing here drops out, right? This is just white noise. So actually what we can write is that the expectation of ET plus 1 is just equal to phi times ET. Okay, so we're going to use that here to change this ET plus 1. And then I'm also going to cross out the alphas here because that's just a constant. Okay, so let's rewrite now. Before I substitute in the big expression for KT plus 1 here, let me just rewrite that. Now we're going to have beta times the expectation of kt plus 1 plus gamma times phi times et. Okay, so now we have to do the part that's a little bit algebraic here. We have to put in this expression up here. Okay, so let's do that. We have beta kt plus gamma et is equal to beta times the expectation of negative alpha plus a minus beta plus 1 kt plus 1 minus gamma et. Okay, now the good news here is that we know what kt is and we know what et is. Okay, so actually this expectation is going to go away. Okay, so now we're almost, actually I think we can pretty much be, I'll just write it out one more time and then we can start talking about the values of these parameters. So I'm just going to write it out a little bit neater now. Gamma et is equal to negative alpha beta plus a minus b plus 1 kt plus 1 minus gamma et. Plus gamma phi et here. Dropped it out. Too many terms here. Plus gamma phi et. Right, this guy carried through. I dropped it out. Okay, so I think we can now compare these terms. So what we know is that negative alpha beta has to equal 0. There's nothing else here that's not multiplied, right? This thing is multiplied by kt. This thing is multiplied by kt. These two things are multiplied by et. This thing is multiplied by et. So this thing is just, it's equal to 0. There's nothing over here. So the first thing we know is that negative alpha beta is equal to 0, which implies that either alpha is equal to 0 or beta is equal to 0. We don't know which one yet. All right, next thing we know is that beta is equal to a minus beta plus 1. Okay, so we've got beta is equal to a minus beta plus 1, right? And then the last thing we know is that gamma is equal to 1 minus gamma plus gamma phi. Okay, so gamma is equal to 1 minus gamma plus gamma phi. Okay, so I think a good way to solve this is to start with this one here. We know that either alpha is equal to 0 or beta is equal to 0. So from solving this, I know that it's going to be alpha equal to 0, but let's say that beta is equal to 0 and find out what happens. Okay, so if beta is equal to 0, let's write that here. If beta is equal to 0, then 0 equals a plus 1, then 1 plus a equals 0. But that's a contradiction. That's not true. Okay, so that can't be right. So then that means that alpha is equal to 0. Okay, so we've determined that. One parameter done, that's good. All right, down here, let's see here. We have, double check my notes. Question?
Sorry, you kind of lose beta on the second and third term.
Yes, you're right.
For
I forgot to
the
multiply
equation.
by beta.
Yeah.
Thank you very much. I forgot to multiply, pre-multiply by this beta here. Just noticing that in my notes here, but not here. Oh no, it is here too. exactly. Thank you very much for that. All right, so what we're going to get then is that, let's divide both sides by beta. So we're going to have 1 is equal to a minus beta plus 1. Okay, so that means that a minus beta is equal to 0, or that beta is equal to a. Okay, so we've got that. We've got that. So the only thing we don't know now is gamma. So let's solve for gamma. Let's multiply this through so I don't get confused again. Minus beta gamma plus beta gamma phi. Double check and make sure that's what I had before. Okay, so it looks like I didn't need to multiply by this beta here. Let me quick make sure I'm doing this right. Okay. Yeah, so this beta here only multiplies the KT, it doesn't multiply the gamma phi. So actually I didn't need it here. Which means that I don't need it here. Let me write this correctly. This one is going to. Is that what you guys got? It is, right? Let me know if it's not. Okay, so we have to solve for gamma. We should be able to do that. So let's see here. Let's collect all the gammas on one side. We're going to get 1 plus beta minus phi is equal to beta. So we're going to get that oops, what did I do here? 1 plus beta minus phi. I said phi, but I wrote gamma. So the gamma is equal to beta divided by 1 plus beta minus phi. Okay, but we can actually replace the beta because we know the beta is equal to a. So we get a divided by 1 plus a minus phi. Let's see if that's what I got in my notes. Yes, it is. Okay, excellent. All right, so I think that's the end because we've now got gamma in terms of parameters. We've got beta in terms of parameters, and then alpha is equal to 0. So let's see. What values must they have for the first order condition to be satisfied for all values of k, t, and et? So I think that's it. So let me know if you got any questions. All right, and then the last one here, what are the effects of a one-time shock to epsilon here on the paths of y, k, and c? So I didn't really know exactly how to solve this. I mean, one way to do it would be to put it into Excel, but I mean, I think we can just write out the our equations with these parameters now in them. So that's what I'm going to do. So let's first write out consumption. So we solve that first. So for example, this is now D. So consumption is equal to, I'll just write this here. Oops, not ET. A plus beta times KT plus gamma times ET. All right, now we solve those things. So we've got 0, beta is equal to A KT plus A divided by 1 plus A minus phi times ET. Okay, so there's our consumption. Depends on KT. The most important thing, just to continue, let's write out YT because it asked about the path of YT. So that's going to be AKT plus ET. That's just by definition. And then finally, the most important one is kt plus 1. So you recall that kt plus 1 is equal to, let's do it this way, yeah, yt minus ct plus kt. Okay, now we know what ct is, and we also know what yt is, so I can just leave yt actually. So kt plus 1 is going to be, yeah, I guess I've written them both out here, so I don't really need to totally rewrite them, but I will anyway. So let's see here, akt plus et minus akt, interesting, akt minus a divided by 1 plus a minus phi times et, okay, plus kt. So interestingly, these guys cancel out actually. And I end up with kt plus 1 minus a divided by 1 plus a minus phi times et. Let's simplify that last one more step. It's equal to kt plus 1 plus at minus at. So it's going to be 1 minus phi divided by 1 plus a minus phi times et. Okay, so I mean, I didn't actually do this. You could do it in Excel if you wanted, but if there's a shock, if there's a one-time shock, what's sometimes called an MIT shock to excuse me, epsilon t or epsilon, it's going to drive this ET up, and then that ET is going to stay high for a while because it's just this reversion to the mean over time. That's going to cause capital to increase at time t plus 1. And then you can see that, yeah, it's going to cause capital to increase at time t plus 1. And then that's going to cause output to increase and consumption to increase by these factors. You know, that ET shock lasts for a while. So over time, the capital stock will well, it depends on the value of phi. So anyway, you're gonna end up reverting to the mean eventually, but you're gonna have this shock where output increases, consumption increases, capital increases, and you're gonna get this reversion to the long run trend. So I'm not sure if the problem wanted more than that. It's hard to actually do more because they didn't give us values for the numbers of a and you know, phi, which are the fundamental parameters of the model. But I think that this is probably enough. Did you guys do more than that when you were solving this problem? Like I said, you could go to Excel and do it, but you need numbers for that, of course. But this is how I understood it, is just to write out these equations in terms of just the fundamentals of the model and the shocks.
I mean, you could take it further and find the equations with the epsilon in them, and then take the derivative with respect to epsilon. But you need to find the solution equations.
I see. So then I see.
But I couldn't do that, so I just ended up looking at the answers from the book.
I see. Okay. And they did solve it though, all the way to the.
Yeah, they do something like that, but they use some hand wavy stuff.
They do some hand wavy stuff. Okay. This is what I understood when I solved it. Maybe I should take a look at the solution manual. I have a copy of that too. Sometimes I find that the solution manual solves things in sort of a too mathy way. I don't know if you guys have found that, but yeah. Okay, I see. So you'd want to sort of solve out the KT. Okay, well, this is what I did, and this is what I consider correct. So I guess I'll just leave it there. Any questions about this? More than that? I guess you could maybe, yeah, now that you're saying it, maybe you could go a step farther, but not 100% sure. Well, if there's no questions, then I will consider this done. Okay. So thank you very much. And I will see you next week when we're going to talk about the DSGE model in the book, which is what central banks actually use these days for monetary policy. I also mentioned that, in case you care, I'll just mention this one last thing about the pandemic. So I don't know if you guys saw, but they're now restricting a couple of the vaccines. So AstraZeneca is on pause now in Denmark and in many European countries. And Johnson & Johnson, they just put it on pause in the United States and they stopped shipping to Denmark. So I saw on the news that that a professor of, I don't know, something public health something, said that if there's no AstraZeneca and there's no Johnson & Johnson, we shouldn't expect Denmark to be fully vaccinated until the end of this year. So I was very shocked by that, and I'm just imagining another year of online courses, which would not be ideal for me, at least. But anyway, I thought it was really interesting because of how much this resembles this ethical dilemma called the trolley problem. And it's a little bit related to macroeconomics because of the way that we think about social welfare in macroeconomics typically. So I don't know if you guys have heard of the trolley problem, but I can give you a brief sort of version of it. So suppose that you see a train, it's hurtling towards 5 people. And if the train hits them, they're on the tracks, they're tied down on the tracks for some reason, they can't move. If the train hits them, they're all gonna die, all right? And you're standing next to a lever that can divert the train onto another track, okay? But the thing is, on the other track, there's one guy that's like, you know, not looking, or he's tied down or something, and he can't move either. So the question is, should you pull this lever, saving 5 people, but then killing this other person? Okay, so I don't know what your intuitions are. Does anybody want to say what their intuition is in that case? Should you pull the lever? So I'll just say it. So many people's intuitions are that you should pull the lever, okay? Because of course, 5 people dying is worse than 1 person dying, right? So, you know, I don't know if that's your intuition. Some people have other intuitions, but you know, that's the intuitions of many people, I think. And then the fun with the trolley problem comes when you start thinking of other examples that seem similar, but somehow different. So here's one. Imagine that you are a surgeon in a hospital and you have 5 patients that are each going to die without getting a particular organ. Okay, so they need an organ transplant, and they're going to die. If they get the organ transplant, they'll live. Okay, so there's a person coming into the hospital just for an exam, totally healthy. The question is, should you kill that person and harvest their organs and put them into the other people that need organs? Okay, so in that case, most people's intuitions are no. You shouldn't kill a healthy person in order to harvest their organs and put them into people that need organs, okay? But then you have to think, what's the difference between that question and the trolley car question, okay? So the reason I'm mentioning it is because I think it's related somewhat to this vaccine debate. So in the vaccine debate right now, these blood clots that are caused by AstraZeneca and Johnson & Johnson potentially are very rare, right? So we're thinking it's like, several in millions of shots. So, a few per million people that get it will get a serious blood clot and die, maybe. Let's assume that's true. Okay. So, of course, if you don't give the vaccine to people, then people will die from getting COVID. And then in addition, there's all sorts of other types of costs of having, mental stress, whatever costs of continuing this coronavirus crisis. So, it seems like in terms of just a utilitarian trade-off that maybe it's something that we should do, right? We should maybe give people these two vaccines. But it feels different, doesn't it? Because, we're administering the vaccines. There's a doctor that's going to give you a shot. And if you get the shot, that shot might, with some small probability, might kill you. So, I mean, I think that doctors feel like it's unethical for them to be the cause of the death rather than, corona. It's like nobody wants to get COVID. And if it happens, that's really unfortunate. So, it's not really like the doctor is directly harming you if COVID kills you. Whereas if they give you the vaccine and you die, then it was kind of like you wouldn't have died if you hadn't got the vaccine. So, I find that it's very interesting. It's a very interesting relationship with the trolley car problem. Now, why am I mentioning it in macroeconomics? So if you think about macroeconomic welfare calculations, almost always they're based on this utilitarian calculus, right? So it's like, how much consumption, how much leisure, we're going to add it all up, and then we're going to do the thing that creates the most utility. Not the thing that's going to make the most people well off, but the thing that's going to create the most utility in the society, regardless of which person has the utility. From the lens, through the lens of the macroeconomic model, we should always do, we should do pull the trolley car switch, and maybe arguably we should still continue with the vaccine rollout. In fact, I think if you kind of look on the econ Twitter sphere, the econ posts, economist posts, many of them have this utilitarian intuition. So that's all. I thought that was an interesting thing, and it was related to macroeconomics. So I thought I'd mention it to you while I have you. Any comments? Okay, then I will let you go, and I will see you next week.
See you. Bye.
Bye.